All right, so now that we've got a fair foundation here in Chapter 8, we understand solution concentration and other core solution concepts, we can extend our understanding of solutions even further as we discuss a couple new ideas here in Chapter 8. So here in this section 8.5, we'll discuss dilution of solutions and solution phase reactions. So two very important concepts and very important applications not only in chemistry but also the health sciences and any field where you're considering solution chemistry. All right, so dilution. I think you've got probably a handle on this idea of dilution, but when we use the term specifically in our course, it's a process where a solvent, usually water for things that we tend to encounter in Chem 145 and most of the chemistry of living systems is water-based. So we add water or some other solvent to a solution to increase the solution volume and therefore decrease the concentration. We're not adding any more solute, we're just adding more solvent. So if you think about our example we see on the screen, 1 can of orange juice concentrate, if you buy your orange juice like this, it's an inexpensive way to do it, right? Because you're not paying for all that water. Then at home, you can fill the cans after you've poured out the concentrate. You can fill with 3 cans full of water, and now you've reconstituted it. You've diluted it to its original strength from its concentrated strength, and you've saved some money because you're not paying to ship the already made orange juice. You're removing some water at the factory and then reconstituting it back at home. So that's actually a very environmentally friendly and economical way to do things. So as we think about the process, we're adding solvent, so we're increasing the overall volume of our solution, but we don't add any more solute. So the concentration is impacted both visually, if we look at this dye example here on this slide where we have a fairly intensely colored orange-red dye in its concentrated form. As we dilute it with water, you notice that the dye particles get further apart. They become less concentrated there as they're diluted, and the result is a lighter, less intense color because you've got a larger space in between the dye particles because you've got more solvent to fill that space in between solute particles. Now, if we're thinking about finding those final concentrations based on the initial concentrations and then the final diluted volume, what we have to understand with dilution is we're not changing the solute. So the solute is what's in the numerator, right? The moles of solute per liter of solution is our definition of molarity, which is our most common unit for concentration in chemistry. So if the moles of solute are the same, then all we're really changing is the volume. We go from the more concentrated solution that has the more concentrated molar concentration and the smaller volume, and then we can find now once we've diluted it to a larger volume, we can find the new diluted concentration. So this is commonly shown in most textbooks as M1V1 equals M2V2 because molarity is our most common unit of concentration in chemistry. But here in our text we have C1, which could be any concentration, whether it's molarity or whether it's mass percent or mole percent. But again, typically it's molarity. So that first concentration times that initial volume equals the diluted concentration times the diluted solution volume. So this is very useful for dilution. Be careful when we talk about solution phase chemistry. Sometimes people try to apply this formula for reactions, and sometimes it works and other times it doesn't. So just be careful. This is only valid for dilutions. So concentrated solutions, trying to find the concentration now of the diluted solution after some additional volume of solvent has been added. So I'm sure you've gotten used to this. After we talk about a calculation, then commonly we follow up with a guide. So here's our guide to calculating dilution quantities. So first we prepare a table of concentrations and volumes of the solution, so the starting and the final. Then we have to rearrange the dilution expression to solve for the unknown quantity. Sometimes we'll know the initial concentration, initial volume, and we'll be solving for the final concentration or final volume, or we could sometimes even be solving for the original concentration or volume depending on the problem. Finally, we will substitute in our known quantities into that dilution expression and then calculate the unknown. All right, so let's go ahead and have you do a learning check just to see how these concepts are coming through. What volume of a 2.00% mass per volume percent hydrochloric acid solution can be prepared by diluting 25.0 milliliters of 14.0 mass per volume HCl solution? So go ahead and use our approach we just discussed to solve this problem. Let's pause the video here. Once you're ready to check your work, start it back up and we'll hopefully arrive at the same correct solution. So here in step 1, we put the values into a table. So we have our concentrated solution. That initial concentrated solution is 14.0% mass per volume of HCl in water, understood. Then we have a initial volume of that concentrated solution of 25.0 milliliters. Our diluted solution, we know the diluted concentration will be 2.00% mass per volume as well, so same units as our starting concentration, but we don't know how many milliliters of solution we'll have after we dilute that original solution to this new diluted concentration. So we do know that concentration decreases as we dilute a solution, so we expect to have V2 be a larger volume than 25.0 milliliters because C2 has gone down, so V2 must go up from V1. Moving on to step 2, we can rearrange that dilution expression to solve for the unknown quantity. So in this case, it's that final volume, V2, that we're solving for. So we can divide both sides by C2 to isolate V2 and then flip the equation around to get V2 equals V1 times C1 over C2. Finally, in step 3, we can substitute in those known quantities to calculate our unknown. So 25.0 milliliters was the V1 multiplied by 14.0% mass per volume divided by 2.0% mass per volume. So the mass per volume percents decrease or cancel rather. So we get a final value of 175 milliliters, 3 sig figs, just like all our other values. We're only using multiplication division sig fig rule, so 3 sig figs all along gives us a final answer to 3 sig figs of 175 milliliters. Hopefully that's exactly what you arrived at. If not, please do try some additional problems. We'll be doing another learning check in just a moment with molarity, but if you want to try additional homework problems or end of chapter problems, and if you still can't master this concept, please do reach out to me for help. All right, so I told you that molarity is the most common way that we'll see this, and then our first learning check doesn't use molarity. We use mass per volume percent. So now here's a follow-up learning check where you'll see the much more typical molarity expression. So in this learning check, we're asked, what is the molarity, capital M is our unit, remember, of a solution prepared by diluting 10.0 milliliters of 2.7 molar NaOH solution to 60.0 milliliters. So this time we know the starting volume, the starting concentration, the final volume, we're looking for that final concentration. So pause the video here, work that out, and then start back up when you want to check your work, and hopefully we arrive at the same answer. Okay, so here's my table. Hopefully it looks a lot like yours. So in this first step, we're analyzing the problem to find that the concentrated solution, the concentration 1 is 2.7 molar NaOH. The volume initial is 10.0 milliliters. We're not sure what the final concentration is. It's C2 that we're looking for, so that's our unknown, our question mark here. V2 we do know is 60.0 milliliters. We know that C has to decrease because V increased, and of course if it's a dilution problem, then when we dilute, we add more solvent volume to end up with a smaller concentration solution. So we know that we're looking for a concentration less than 2.7 molar because that was our starting concentration, but we're not quite sure exactly what it is. That's what we need to move on to step 2 to solve. All right, so there we are in step 2. This time we're looking for C2, so we can rearrange by dividing both sides by V2 and then flipping the direction of our equation to get C2 on the left, which is the more traditional way to express our unknown. So C2 equals V1 divided by V2 times C1. And now moving on to step 3, we can substitute in those numerical values with their units. So 2.7 moles of NaOH per liter of solution times 10.0 milliliters, that's V1, divided by 60.0 milliliters, which is V2, gives us a final solution concentration of 0.45 molar NaOH. So we have 2 sig figs for the starting concentration, 3 sig figs for the starting volume, 3 sig figs for the ending volume, but because of our division and multiplication rules, we end up using the least significant figures. So the 2 sig figs from our concentration 1 ends up giving us 2 sig figs in concentration 2, 0.45 molar NaOH is indeed less concentrated than the 2.7 molar NaOH we started with. So that's a good logical check, and hopefully that's the same answer you arrived at yourself. If not, please do seek out some other problems, seek out my guidance. It's not going to go away or get better on its own, so let's address any issues you might have and make sure that you're ready for the homework sets and exams and all those good things that we'll be using this concept for. All right, so now that we hopefully have a pretty good handle on dilution expressions and how to solve for diluted volume or diluted concentration, let's take a look at solutions in chemical reactions. So solution phase reactions are quite common when chemical reactions involve these aqueous solutions. Typically, molarity and volume can be used to determine the moles of substances either required or produced. And again, solutions are convenient because the reactions are ready to react. So instead of waiting for things like solid metals and solid compounds to react with one another, when you get them into the solution phase, they're very reactive. Things happen much more quickly. So that's why solutions are very common in chemical reactions. So we see here on our image, there's a solid zinc metal reacting with HCl solution to produce some zinc chloride, which is dissolved in the solution, as well as hydrogen gas. That's the bubbling stuff that you see escaping the solution. So solutions are very, very important in many chemical reactions. All right, so here's a guide, and this is a little more involved, right? It's a 4-stepper, but nothing above anybody here in this course. So first, we're going to state the given and needed quantities. Just like any time, we're going to analyze our problem. This time, it happens to be a solution in chemical reaction problem. For step 2, we'll write our plan to calculate whatever the needed quantity or concentration might be. Moving on to step 3, we can write our equalities and conversion factors, including mole, and concentration factors from the balanced chemical equation. And then finally, now in our 4th step, we're ready to set up the problem to find our needed quantity or concentration, whatever it may be. So very typical setup for what we've been using in this course is our guides, and hopefully it's one that's not too difficult to extend to solution chemistry. Okay, you knew it was coming, right? Here's a learning check. So here's your first chance to see how you do with this concept and see how you apply that guide. How many liters of 3.00 molar HCl are needed to completely react with 4.85 grams of calcium carbonate? And we have our balanced chemical equation telling us that 2 moles of hydrochloric acid react with 1 mole of calcium carbonate solid to give 1 mole of calcium chloride solution, aqueous phase, plus 1 mole of carbon dioxide gas, some of which will escape as bubbles, a little bit of which will dissolve into the solution as well, and then finally liquid water. So using the information in this problem, go ahead and solve for the liters of HCl needed. Stop the video here, start back up when either you've come up with a solution or you've become frustrated because we didn't do a problem together first before I threw you into this learning check. All right, so here we go. Step 1, we're analyzing the problem here. We know that we're given 3.00 molar HCl as reactant 1, 4.85 grams of calcium carbonate as reactant 2. We need to know how many milliliters of that HCl solution we would need. We also will need to know the molar mass of calcium carbonate. That one we can calculate from the periodic table, though. And finally, our equation, we have the balanced chemical equation given originally in the problem to give us our mole-mole ratios. Moving on to step 2 here, we'll write our plan. So we're going to take that mass of calcium carbonate, the 4.85 grams that we're given to start with. We'll use the molar mass to find the moles of calcium carbonate that mass contains. We'll use the mole-mole factors from the chemical reaction to find out how much HCl is needed to react with that number of moles of calcium carbonate. And then finally, we'll use the molarity of the HCl solution to find out the liters of HCl in order to solve the problem. That's exactly what the problem is asking, so that's our final solution. Moving on to step 3 here, we'll write our equalities and conversion factors, including those mole-mole and concentration factors from the problem. So 1 mole of calcium carbonate equals 100.1 grams of calcium carbonate. Hopefully you found that rather easily now by adding up the molar masses of calcium, carbon, and 3 times oxygen from the periodic table to get the 100.1 grams per mole. So we can express that with either the mole in the numerator and the 100.1 grams down in the denominator, or vice versa. Obviously, if we're starting with the 4.85 grams, we're going to want the grams in the denominator for canceling purposes. We also know that 1 mole of calcium carbonate reacts with 2 moles of HCl based on that balanced chemical equation. So we could have that in either form with calcium carbonate on top, or the HCl on top of our expression, depending on what we need. And of course, if we end up in moles of CaCO3 after we've converted our mass in grams into moles, then we'll want mole of CaCO3 in the denominator. Unfortunately, we ran out of space on the last slide, but one other equality that we have based on the information in the problem is that 3.00 moles of HCl equals 1 liter of this HCl solution, right? That's what the 3.00 molar HCl is telling us, that we have 3.00 moles per liter. So we can either have the liter in the denominator or the liter in the numerator, and the 3.00 moles would go wherever the liter is not, in order to make the equality into a conversion factor. So obviously in this case, since liter is our final answer, liters of HCl solution, we'll need the 1 liter of HCl up top and the 3.00 moles of HCl in the denominator. All right, here we are in step 4. Now we're ready to set this thing up. We start with that 4.85 grams of calcium carbonate. We multiply through by the conversion factor 1 mole CaCO3 over 100.1 grams CaCO3 to cancel grams of calcium carbonate and be left in moles. Now we can multiply through by 2 moles HCl per 1 mole of CaCO3 to cancel the unit of moles of CaCO3 and be left in moles of HCl. We now multiply through by the 1 liter HCl per 3.00 moles HCl, and we are now finally in the unit of liters of HCl solution, which is exactly what we want. As we handle the numerical end of things, we should find that we end up with 0.0323 liters of HCl required. And the question specifically asked for liters. Of course, we could also say that we want 32.3 milliliters if the question was not specific to liters. So there we have it. Hopefully it was fairly easy for you. And of course, the final number there, sig figs, were really based on the 4.85 and the 3.00, each having 3 sig figs. So our final result has 3 sig figs as well. If this was a little challenging for you, don't worry. We've got another learning check right ahead. Okay, here it is. As promised, we'll round out this section of the chapter with a final learning check. So in this case, if 22 milliliters of 0.10 molar magnesium chloride is needed to completely react 15 milliliters of silver nitrate solution, what is the molarity of the silver nitrate? So we have our balanced chemical equation: 1 mole of magnesium chloride, aqueous solution, plus 2 moles of silver nitrate in aqueous solution yields 2 moles of silver chloride solid plus 1 mole of magnesium nitrate solution. So go ahead, stop the video here, try your hand at working this problem, and then start us back up when you're ready to check your work. Okay, just like before, we're going to use step 1 to analyze the problem. We're given that we have reactant 1, 0.10 molar magnesium chloride solution. We're also told that there's 22 milliliters of it. And if we wanted to convert it, because we obviously will need to at some point, we find that 22 milliliters times 1 liter over 1,000 milliliters gives us 0.022 liters of MgCl2. For reactant 2, we know that we have 15 milliliters of that silver nitrate, and we can convert that as well by ultimately dividing by 1,000, right? Multiplying by 1 liter over 1,000 milliliters gives us 0.015 liters of silver nitrate. What we need to know is the molarity of that silver nitrate, and we're also going to make use of that balanced chemical equation that was given to us in the problem. All right, moving on to step 2, we'll write our plan. So we're going to start with our volume of magnesium chloride and multiply through by the molarity of the magnesium chloride to find the moles of magnesium chloride. Then we can use the mole-mole factor that relates magnesium chloride to silver nitrate, in this case 1 mole of magnesium chloride per 2 moles of silver nitrate factor. That will get us to moles of silver nitrate, and in order to find the molarity of silver nitrate, we'll take the moles of silver nitrate divided by that 15 milliliter volume that we've converted into 0.015 liters. Moving on to step 3 here, we can write some equalities. In this case, we know that 0.10 moles of magnesium chloride equals 1 liter of that magnesium chloride solution. We also know that we could express that as an equality, a conversion factor now rather, with 0.10 moles of MgCl2 in the numerator and the 1 liter in the denominator, or the inverse. We also know that 1 mole of magnesium chloride equals 2 moles of silver nitrate based on the balanced chemical equation, and therefore we can express that either with the 1 mole MgCl2 in the numerator and the 2 moles AgNO3 in the denominator, or the inverse, depending on what will get us the units canceling in order to give the desired final unit. All right, finally here in step 4, we can start with our 0.22 liters of MgCl2, multiply it by the 0.10 mole MgCl2 per 1 liter of MgCl2 to cancel liters of magnesium chloride and be left in moles of magnesium chloride. Then multiplying through by the 2 moles AgNO3 per 1 mole MgCl2 from the balanced chemical equation, we see that that would require 0.0044 moles of silver nitrate. To find the molarity of our silver nitrate, which is what the question was actually asking, we would take that 0.0044 moles of silver nitrate divided by the 0.015 liters of silver nitrate solution from the beginning problem, and we find that that gives a molarity of 0.29 molar silver nitrate. So again, just a matter of following units, setting up the problem correctly, and lastly making sure that we follow our sig fig rules. We had just 2 sig figs for everything that was given, 22 milliliters of 0.10 molar magnesium chloride and then 15 milliliters of the silver nitrate. So all of our numbers were 2 sig figs. We only did division and multiplication, so we would want to have a final value to 2 sig figs as well. So again, hopefully you've gotten the hang of this. It's not terribly difficult, but there are some learning curves here, and if you're still struggling, you shouldn't feel badly. You should certainly try some additional problems, and don't hesitate to reach out to me for help if I can be of any assistance. Otherwise, I'll see you for the next and last section of Chapter 8.